Today I'm going to show the continuation of our stress transformation explanation in the previous video. And now, actually there are three ways of question going to be asked for stress transformation. You're going to need the equations that we have reviewed in the previous video, and solving that requires you memorizing the equation, and you start to calculate the principal stresses. Another ways of solving, and there are two more ways of solving it, which we're going to capture that today by learning a Mohr circle, the method by using Mohr circle. Mohr circle, there are two types of it, by using graph paper and also by sketching it on the paper itself. So for this one, as an introduction, a Mohr circle is a unique way, versatile way of solving stress transformation, whereby you're going to use the properties of the circle to solve either by sketching and estimating. Of course, we can use the rules of the triangles, and by using another way of doing it by using the graph paper. Usually in the examination, you're going to be supplied with graph paper in the test or in the final exam, provided that this question requires you to do so. If it is stated in the question, they're going to supply that. At least that is what that is the practice that we are doing in School of Mechanical here. So learning by solving them by these three methods. We have been in the previous example, we did that by calculations by using the equations. Now we're going to get to know the Mohr circle, the properties, and how to draw. And I'm going to jump in by tackling the same question and try to solve it through Mohr circle. Of course, by using tangible example, it is more doable. So continuation with we are still under stress transformation, but now with Mohr circle. At least I'm going to give you guys two examples. One of them in this introduction video for Mohr circle. We're going to use this the same value that we have before, and perhaps another example I'm going to give you from the second video for revision of combined loadings. You can go to that example, and continuation of that we're going to use the same stress element, and from there we're going to solve by using Mohr circle. So alright, so we have this Mohr circle. It is a method developed by Otto Mohr in quite a while ago, in 1880s. A unique character found in the excess of sigma, which is we know sigma as our normal stress, and also on the y-axis is the shear stress. By plotting on the same Cartesian chart, and we draw a circle from a point, and we from the properties of the average stress becomes the center point of the circle, and we can develop a plane, the properties of the plane for particular axis x, y, and z. So I'm going to show you that exactly that. But first of all, we're going to know the properties of Mohr circle, and I'm going to start with the same element that we have before, which is right the if you can remember the values from the previous example. We're going to have going to try to create the straight line over here. For the shear stress, I can speed up a little bit on that. So this is my supposed to be linear over here, right? For the compression. Alright, and we have a positive axis of x, a positive y, and I'm going to plug in all the values over here. They are 20 megapascal for sigma x. We have 10 megapascal downward, and last but not least, we have 30 megapascal for shear stress of our stress element. And on the x-axis it is theta equal to 0 degree, which is the reference axis for our stress element. So the previous question is asking us to calculate by using the equations the principal stresses sigma 1 and sigma 2, and draw its RVE. And in similar thing, we have over here number 1, principal stresses, and draw RVE. I'm using the same example to show that. So the continuation of the learning is going to be relate. You can easily relate with the previous example. In plane shear stress, and we need to draw RVE for this property also in plane shear stress. So going step by step for drawing Mohr circle, you're going to need, first of all, establish. So this is step by step. You have to jot it down whenever you are answering the next time you meet Mohr circles question. But this is a good way of remembering because this is a stepwise of solving Mohr circle. And define stresses. You're going to do the same thing, identifying x, y, and z, the stresses on that direction, and also as well as the shear stress from our stress element. And in order to draw a Mohr circle, first of all, you need to draw the coordinate, the axis, coordinate axis, which is which one is which, the direction for positive normal stress and shear stress. Number 4, you need to locate the center. And point on outer radius. If you guys are familiar with CAD modeling, to draw a circle, we need to have at least 2 points in order to create a circle. It could be the center and the outer point, which is pointed in point number 4, or we can simply have the 2 points that you're going to use the method of tangent, where you're going to draw 2 lines to get the point, the center point of that out of that 3 points. So simply in order to draw a circle, we need to have at least 2 data or 2 data points in order to draw. Then only we can draw our Mohr circle. Alright, the beauty of Mohr circle, whenever you have the circle, you can pretty much answer the characteristics of the stresses on the stress element. Alright, so the solution for this I'm going to begin with define the stresses. We already for the first one coordinate system. I've done that, which is this done positive x, positive y, positive going outward, and the perhaps second one in order to solve this is to define the stresses. They are simply sigma x equals to 20 megapascal, sigma y equals to negative 10 megapascal. This is the sign convention that we are using. Tau xy, none other than 30 megapascal for our stress element. And in order to draw a Mohr circle, of course I need a space, a little bit of space of for the third step, right? So the third step, we're going to we have defined the stresses, draw a coordinate axis. So I'm going to jot it down here for the third step, coordinate axis for our Mohr circle. Right, so I'm going to make sure because this is explanatory video for Mohr circle, so should be generous with the space, right? So first of all, I'm going to draw the first axis, which is the positive for my normal stress is going towards to the right, right? So this is my which is positive sigma. I'm going to put it over there, and going downward. So this is my positive tau, which is shear stress. So now it is important to when we have Cartesian chart like this, it is super important to make sure the what we call the scaling that we are using is proportionate. It is easier, of course, it is easier when plotting on the graph paper, but what we are having right now, the introduction for Mohr circle. So I'm going to go ahead and locate my point number one, which is by using this information of 20 megapascal and 30, which is be careful, we are having two axes over here, sigma and tau, which is shear stress. So if I can say this is my scaling that I'm using, 10, right, 20, 30. So my first coordinate is 20, 30, which is positive to the right and downwards, right? So I'm going to say my point A is 30 over here. So 30 positive x is 20, and as well as the positive 10, 20, 30 for my shear stress. So I'm going to locate my first coordinate is over here, 20, positive 30 over there. That is my point A. Say point A for my first coordinate. Going to put on each side, locating that this is 20, 30 coordinate. So then what do we need after that? We need to locate the center. How do we locate the center? So this is where point number 4 came in to locate the center. Center and first point on outer radius. So the way of doing this, of course, the center for our Mohr circle, remember it is the center is the sigma average 0, this is the coordinate. So it is easily, if you can recall the previous example, we have calculated the average of our system right here. 20 plus negative 10 equals to 10 divided by 2, it becomes 5. So we already have that value before 5 megapascal. I'm going to do it again here to make it super clear. Sigma average is equals to sigma x plus sigma y over 2, and as I mentioned just now, 20 plus negative 10 over 2, and it gives you 5 megapascal. So this is our sigma average, which is the center point of our circle. Now I'm going to and yeah, it is worth mentioning here, A is sigma x, tau x, y, our first coordinate that I've jotted on the Cartesian chart, which is 20, 30. Of course, the unit is megapascal. So, and by using the, actually, if you already have that, so we already located our center, which is, I'm going to put it in here in red. This is our center, which is the coordinate is 5, 0. So basically, if you have these two lines on your chart, you can simply draw a straight line. Just want to show you that what we're going to have over here is, yeah, I think that's about right. Yep. So of course, this is estimation. The best way of doing Mohr circle is by using the graph paper. But by using this simple example, we already have the points. So I'm going to finish up with to identify a few values that we have before, and plotting on the coordinate system. Now this is our sigma 1, 0, which is our major stress, and the other side will be our sigma 2. Sigma 2 is our minor stress, also a coordinate system, sigma 1, sigma 2. That is what you are seeing. The value is negative 28 something, right? So I think it is helpful if I can plot, list down everything over here, so you can see on a visual right here. So step number 4, we already locate the center and the outer point of our circle. Number 5 is our radius of circle. Right, to draw our radius of circle is equals to the R. I've already located the by using the purple letter of R. So R is equals to 50 square plus 30 square. So how do I get that 15 and 30? 30 is just right. I'm going to show it clear over here. This triangle over here is where we have 15 is coming from. 15 came from this side over here, which is 20 minus 5. This gives you 15, and 30, of course, the length of this side over here. This is 30. So this is 33.54 megapascal. So the value for your R is the radius 33.54, which is equals to the maximum shear stress that we're going to do a follow-up later to answer question number 2. And of course, principal stress need to be shown here too. Principal stresses, because in order to answer all of the question, so sigma 1 is equal to sigma average equals to 5 plus 33.54. It gives you 38.54 megapascal. Alright, and sigma 2 is equal to sigma average, this time around minus the radius. 5 minus 33.54 megapascal gives you negative 28.54. Right, negative 28.54 megapascal. So we have those values. Of course, you can locate that values in your on your plot, but this is what we have right here. The radius and the locations of principal stresses 1 and 2. What else that we should mention here again to have a look on your Mohr circle right here. So I'm going to this is sigma average. The center point is our sigma average. From that point to your outer point of your circle, which is this one sigma 1 here, this is your R. So it is just properties of our circle plotted on the y axis, but now x and y is replaced by normal stress sigma and shear stress tau, which is pointing to the right positive and downwards positive for our shear stress. So this is our sigma average over here. After the Mohr circle is plotted, so we can now identify and draw our RVE. For this particular example, we have calculated our angle for principal stress 1 is equals to 31.72, which is actually basically the angle, the half of the angle of theta P1. How was theta P1 is defined is from the angle from the solid purple line to the theta equals to 0 degree. This is alpha. This is where theta P1 came from. So from here, theta P1 is equals to alpha over 2. So by using trigonometry, you can calculate this alpha, and by using graph paper and the compass and protractor, you also can calculate the value, the angle of alpha, and by using the equations also you can calculate the alpha. So basically we are using tangent equals to 2 theta p, tangent 2 theta p equals to 2 tau xy divided by sigma x minus sigma y previously. Actually, basically that is the definition of trigonometry we have for this example. So by using that alpha for this particular example, we have previously 63.44 degree. That is the alpha. So from there, I can calculate my theta P1 is equals to 31.72 degree. So it is more obvious when we draw our RVE. So the angle 31.72 degree in Mohr circle is half. The angle for theta P1 is half of the alpha in Mohr circle. So they are two related. So I'm going to draw my box over here by using perpendicular angle towards my slanting angle 31.72 degree, which is theta p1. And if you're wondering, right, so there are two angles for my answer previously. So for this one, I'm going to finish off with labeling the principal stress one equals to 38.54 megapascal, and compressive minus stress of 28.54 megapascal. So for this particular example, we have this value, and if you notice that we have another angle which is coming from this angle. So I'm going to denote that as theta p2. So in Mohr circle, where does that line, that angle came from? It is coming from the angle. I'm going to denote that by double line of for point A, which is the value is 243.44 degree, which is the summation of 180 degree plus 63.44. So on Mohr circle, the location is this angle right here that I put with double angle notation right there. That is our theta p2. So you can call it also, which is this is 2 theta p2, or simply I can call this as beta. So the other value for that, if you sum it up 180 degree with 63.44, you will get the value of 243.44 for your beta. And for that, you will get your second theta p2 right here, which is half of the beta, beta over 2. Theta p2 equals to 243.44 degree divided by 2. You will get your theta p2 as 121.72 degree, which is another angle of our RVE. So two representations, RVE and the Mohr circle, they are both related, and I would like to indicate also 180 degree towards the point of A. You're going to get your point B, which is for Mohr circle. You can indicate that B is on the same stress element that we are given. So basically B is 180 degree point opposite of A, and the coordinate over here we can call it sigma y tau xy. Interesting enough, the point B is 180 degree, which is on the same plane, and the value, if we draw properly on the graph paper, you will get this coordinate right here. So this is negative 10, this is negative 30. So basically sigma y is exactly the stress element that we are given, which is negative 10 and negative 30 in terms of shear stress for that point. So last but not least, for this particular example, the second part of that question, maximum in plane shear stress, which is also can be drawn by using Mohr circle. We plotted previously with the coordinate of 20, 30 for positive tau and positive sigma, and roughly the location over here for our point A, 20, 30. So out of this circle, we have drawn our circle in the solution. So and 5 megapascal is our semi-average. So now we have our point and at A. So this is our semi-average is located, which is 5 megapascal, and which is the center point of our circle. And from this uh, center point, you can draw a line, and at this particular point, the maximum in-place shear in Mohr circle can be denoted as the furthest point on the top and the bottom of the circle. So we can call this semi-average, tau max, the coordinate for this. And from our previous calculation, we simply have our tau max is equal to R, which is 33.54 megapascal. So basically this is the radius, the blue dotted line, sorry, the radius from point to sigma 1, 0. Also we can call this the radius, which is along the circle that is the furthest point from the top and the bottom of our circle. So to simplify, this maximum in plane shear can be simply said tau max is equal to 33.54 megapascal, which is also the radius of our Mohr circle. You need to remember, we need to draw the RVE for this also. And I think the only thing missing in my explanation here is the angle for our theta S, which is the theta for the shear stress. So if we can take as for this particular drawing right here, the angle for shear stress is basically theta S, what we are looking for. The angle that we can denote on the Mohr circle is this. This is, let's say, I'm going to call this as phi. So theta is simply phi over 2. So again, we can calculate that by saying that if we have this as alpha, alpha equals to 60 from the our previous answer for 63.44. It is simply 90 minus 63.44. So you will get your phi, basically phi is 90 degree minus alpha, which is 90 minus 63.44 degree. You have your phi as 26.56 degree. So by dividing that by 2, you will get your theta S as this theta S is equal to phi over 2, 26.56 over 2 comes to 13.28 degree, and the direction is going, because it is underneath of positive sigma, so it is like that, clockwise. So by having that value, we can draw our RVE, right? So by using that value, 13.28 degree, right? So going to draw perpendicular to this slanting angle. Can I have our, this is theta equal to 0 degree, 13.28 degree, and this is, I'm going to call 5 megapascal for sigma average on this direction. Similarly to this direction, also 5 megapascal. And our shear stress, the maximum tau max is 33.54 megapascal over here. And by having that, this is our RVE for the plane stress element in the max in plane shear stress state. So likewise, we for principal stress, we have two values for the angle. For shear stress also, it is basically the same. So the other angle for that is, we have the second angle is this, which is 76.72 degree on the stress element. Theta S can be computed by using the equation tangent to theta S is equal to negative sigma x minus sigma y over 2 tau xy. But on the Mohr circle is what we have represented. The phi is calculated by using the angle from the vertical line to the solid purple line, where A, our coordinate of 20, 30 is located. So the angle of that is our phi, whereby theta S shear stress angle is defined. So this is the plane stress, the answer for the plane stress element in the maximum in plane shear stress. Look at the value for total for the sigma average is representing all the normal stress on in every direction. So 5 megapascal is also the value for on the x direction, or as well as on the y direction. So that is basically the example for a Mohr circle. I'm showing the calculation for the similar with the previous example by using the equations, but this is the plot of a Mohr circle to help us to answer. If you can recall, they complement each other. The Mohr circle is exactly the representation, the visual representation of the mathematical equations that we have learned in stress transformation by using the equations. So I think that is all for this example. I hope this going to help you a little bit with the Mohr circle. Take it easy, and see you in the next video. Thank you.